Resistance welding equipment consists of a power source and two water-cooled electrodes. The heat source is provided by the electrodes, which conduct electrical current through the sheets of metal being joined. The melting occurs at the interface of the sheets of metal due to the resistance to the flow of electrical current. When the current is turned off, the metal cools, resulting in a welded bond between the two pieces. As noted earlier, the electrodes are water-cooled to prevent overheating. No shielding is required due to the rapid local heating and cooling, along with the pressure applied by the electrodes, which prevent contamination from entering the joint. Filler metal is not required in resistance welding, and we always use the lap joint. To start the operation, the operator ensures all settings are proper. He assures the correct electrodes are installed. Test coupons are then welded. This is followed by a peel test to verify adequate fusion.
In plasma arc welding, metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch polenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application. Ultrasonic welding is a method of producing lap joints by high-frequency vibratory energy and moderate force. This induces interatomic attraction and metallurgical bonding at the weld interface surfaces with relatively little heat. The workpieces are clamped between two welding tips called sonotrodes or jaws. Vibratory energy is conducted through one or both tips, which oscillate laterally as a perpendicular force ensures contact of the workpieces. The oscillating action disrupts the interface surface films and permits metal-to-metal contact. This creates plastic deformation at the interface, resulting in a solid metallurgical bond. Under proper conditions, interface temperatures reach only 35 to 50% of the workpiece melting temperature. Basic equipment includes an electric power supply, a frequency converter to increase line frequency to generally 15,000 to 75,000 hertz, one or more transducers to convert that power into acoustical power of the same frequency, a coupling system to transmit the acoustical power to the welding tip and into the workpieces, a workpiece support system, and a force application system. Ultrasonic welding typically requires at least one of the workpieces to be thin. The usual welds are spot welds and straight or circular seam welds. Workpiece distortion is limited. Ductile metals in similar or dissimilar combinations are ideal workpieces, although hard metals also can be welded. Filler metals are not normally required, although they can assist in joining difficult to weld dissimilar metals. The electrical and electronics industries are the principal users of ultrasonic welding. Limited applications are also found in the automobile, nuclear, and aerospace industries. In electron beam welding, the coalescence heat is generated by the kinetic energy of a focused stream of electrons directed upon the joint. The electrons are produced by an electron gun, accelerated to high velocity, shaped into a beam by electrical fields, and then further collimated or made parallel and focused by an electromagnetic lens. This electron stream is developed in high vacuum, but actual welding can be performed in either high vacuum, partial vacuum, or standard atmospheric pressure. Because of the intense and concentrated heat generated, total heat input is low, minimizing heat-affected zone size and part distortion. This also allows for the creation of extremely deep and narrow welds. Additionally, joints inaccessible by other welding processes can be welded. Virtually all ferrous and non-ferrous metals, thin or thick, can be joined. Welding speeds are fast, and filler metal is not generally required. Equipment cost for electron beam welding is typically high, and welding is generally limited to machined parts assembled in primarily butt, corner, and lap joints. In submerged arc welding, a bare, continuous consumable electrode wire, shielded by a layer of granular flux particles, sustains the arc. When the arc is struck, the tip of the electrode is submerged in the flux, and the arc is not visible. Welding proceeds without the intense radiation that characterizes open arc processes, and with little fumes. The submerged arc welding process varies from semi-automatic to fully automatic. Equipment includes automatic wire feed devices and joint tracking systems to move either the welding head or the workpiece. Submerged arc welding is commonly used to join all types of steel, stainless steels, and nickel alloys. Gas tungsten arc welding uses a non-consumable tungsten electrode and externally supplied inert gas shielding. The most common shielding gases used are argon and helium, and mixtures of the two gases. All types of steels and most non-ferrous metals can be welded in all kinds of joints and positions. Depending on the application, workpieces can be welded without a filler metal or welded with a filler metal supplied separately to the joint. The gas tungsten arc welding process employs either an alternating current or direct current power source, depending on the type of metal to be joined and its thickness. Some power sources provide pulsating direct current with variable frequency. These adjustments allow better control of the molten weld metal when welding thin sections and when welding in other than the flat position.
To arc weld, we need a source of electrical energy, an electrode to carry the current to the workplace, and a grounding device to complete the circuit. The torch head also dispenses a shielding gas, usually argon or helium. The gas prevents air from getting at the molten metal, which could contaminate and weaken the weld. The process starts by adjusting the generator to provide the proper electrical current. An arc is struck by bringing the electrode near the workpiece. The arc causes sufficient heat to melt the metal. Temperatures from 2400 to 5000 degrees Fahrenheit are common. The invisible gas shield protects the molten pool from contamination.